Hello. Welcome to Energy Efficiency and Low Carbon Solutions presentation and workshop. I'm Angela Parker, the City's Sustainability Project Coordinator. So this event is part of the City of Cornwall's annual Earth Week. And for this Sustainable Buildings Workshop, we have a panel of builders and energy experts who will present on building history, advancements, airtightness, and other related topics. So this event is being hosted in collaboration with the River Institute's Science and Nature Speaker Series, and the presentations this evening are being live streamed by the River Institute. So welcome to everyone who is joining us online. And if you are joining us online and have questions for the speakers, please feel free to ask them in the chat, and we will try to get them if there is time. Science and Nature is a hybrid Cornwall-based speaker series that invites experts from different backgrounds to present to the community about their work. You can find out about upcoming events by following the River Institute on social media and checking out the Science and Nature page on their website. So after the presentations, those joining us in person will break out into groups to allow for more intimate discussions with our presenters. In 2023, the city released its first climate action plan. The plan outlines a strategy to achieve the target of 40 to 45% greenhouse gas reduction by 2030 and to become net zero by 2050, community and corporate-wide. Tonight we have joining us Brock Wilson and Jeremiah Point, both certified passive house designers, Stefan Magnaron, registered energy advisor and net zero and passive house consultant, and Jesse Good, the chair of Cornwall's Environment and Climate Change Committee, who will share some of his personal journey to electrification. So the Passive House Standard is a rigorous performance-based approach to building design that prioritizes energy efficiency, comfort, and sustainability. It was developed in the early 1990s by Dr. Wolfgang Feist in Germany and has since become a global benchmark for ultra-low energy buildings. The principles of passive house design aim to minimize a building's energy consumption for heating and cooling, reduce its carbon footprint, and ensure a high level of comfort for its occupants. So I'm going to pass it on over to Brock Wilson, who will start talking about, I forgot the slides. There we go. That was my slide. And now this is going to be Brock's slide. Big arrow. Yes.
Hello. Can everybody hear me? Hi. How are you? First of all, thank you, Angie. Thank you, Jesse, for having us here. What a great introduction too, and thanks everybody for coming here for this Earth Week and our Sustainable Workshop. Of course, Angie just gave you a quick introduction of Passive House, one of the world's most energy efficient standard, highest energy efficiency standard today. So I myself am Brock Wilson, founder of Wilson Architectural Design. I've been working in the architectural industry for over 15 years. I'm a certified passive house designer and have been working in the community on multiple passive house designs and construction, moving forward for high energy efficiency. So with regards to passive house design, just a quick overview. There is 5 particular principles that we'll be focusing on today. Myself, Jeremiah, and Stefan, and we'll run through those each in detail. So these are the 5 principles up on the screen right now. We've got number 1, which is super insulation, so high energy efficiency with super insulation. Air tightness, high performance windows and doors, so your exterior openings. Thermal bridge free construction. We'll get a little bit into detail on that. Sounds a little bit techy. And then mechanical ventilation and heat recovery. So what I'll do is, hopefully I can do this. There we go. First topic, super insulation. So on the screen here, you can see a quick little diagram of a small house. I mean, this could be applied to big houses. And I'd like to also point out the fact that passive house isn't necessarily geared towards houses per se. Passive house is actually a German term, house for buildings, right? So sometimes we can confuse the word house for an actual house, but it can actually be applied in commercial buildings too as well, so just bear in mind with that. So the key features of super insulation is high R values, which an R value is the thermal resistance value of a material. So the thicker the insulation, the better the heat won't escape essentially from that house. So it's essentially whenever you put on a thick coat, you can understand that your heat is going to stay within the coat, keeping you nice and warm. The other key factor is continuous insulation. So we need to make sure that that layer is continuous so that there's no breaks into that. And that will segue into the thermal bridging aspect of passive house. But the key aspect of it is to make sure that it's continuous. As I mentioned, it's thicker than conventional insulation. So if you think of your traditional houses, for example, we have thin exterior walls. Sometimes we put some exterior insulation. Actually, by building code, we do require some continuous insulation on the outside, but it's relatively thin, roughly about 1 inch. So now we're going to a little bit more of an extreme, 4, 6 inches, 8 inches, et cetera. And some typical materials that you'll see with respect to insulation, and we do have some examples here that we're going to toss around so everybody can feel the tactile elements of this. One is, we call it a SIPS panel, which is a structural insulated panel. Essentially, it's OSB, which is a sheet material with insulation in between, which gives you that continuity and thickness that we need. You'll see there's a EPS, which is extruded polystyrene foam slab edge. So essentially, that's our floor of our home that creates that continuous insulation from the bottom of the floor to the vertical portion, which then connects to your wall. So as you can see that we don't only just focus on the walls, we focus on the floors, and we focus on the roof. So making sure that entire area is continued. All right. Sorry, I'm on my phone at the same time, going through the slides. So again, why do we do this? What is the benefit of doing continuous insulation and thicker insulation? Well, it benefits our energy demand. So what it's doing is it's reducing the amount of energy that we need in terms of heating in that case. So again, as I mentioned, putting a coat on and keeping the heat in, well, that's going to reduce the amount of heat that we need to consume, or energy that we need to consume, sorry, to keep that heat in. So again, that will contribute to lower greenhouse emissions in terms of using fuel. In addition, thermal comfort is an item. So walking by an exterior corner of your house, you won't feel a draft, for example. You won't have to put on a sweater. So that intangible that you can't really necessarily pay for or have to pay for is that thermal comfort, making sure that you're keeping that same constant temperature throughout in your house, of course. A couple other things is preventing condensation and mold. Well, if our corners are cold and we have high humidity levels in our house, we can introduce, or that'll introduce potential mold, which is bad for our health and indoor air quality. And of course, I jumped ahead, so improved indoor air quality. Noise reduction, so that's another nice thing. If you have noisy neighbors and you don't want to hear them, well, this continuous insulation and thicker insulation on the outside walls will help mitigate that noise. And sustainable living, as I mentioned, it's reducing your energy consumption, which then reduces the amount of fossil fuels that we need to burn if we're using gas. In passive house case, typically the main source is electric heating. And then long-term cost savings, again, that's going to add up to cost savings as fuel gets more pricier. We're not using as much. So obviously that's money in your pocket. So what I'll do, I think that's it for insulation. I'm going to toss this over to Stefan, who's going to be talking about air tightness.
Thank you very much. All right, so my name's Stefan Magron. Does this work? Everyone can hear me? Do I have to hold it up really close? Yes. Okay, all right. Thank you. First time holding a mic. No. My name's Stefan Magron. I'm from HomeSol Building Solutions in the Ottawa area. I'm a master energy advisor and a passive house consultant. I've been doing this for about 15 years. Air tightness is a wonderful topic for me to cover because I've done a lot of air tightness testing. The benefits are huge. Am I going the wrong way? The benefits of air tightness testing is huge. The reason why air tightness testing came into building code was because of building durability. That's first and foremost. But energy efficiency is a byproduct of great air tightness. So building durability, the amount of moisture that goes through the wall assembly or the insulation that Brock was just talking about, 300 times more moisture goes through an air leak than it does through vapor diffusion. So we focus a lot of attention on the vapor barrier and vapor this and vapor that because we have mistakenly confused a product that does both duties as being more important than what the task it's actually supposed to do, which is air tightness. So by focusing on air tightness and the details allows us to achieve all the benefits that come with it. Building durability being one of it. Comfort is another one. So we're all familiar with the sensation of a draft in the winter. If we don't have any air leaks, there are no drafts, and so you have greater comfort. Another benefit of greater air tightness is when we do a calculation for the size of the mechanical system, the air tightness measure gets added to it as part of the calculation, and the less air leakage you have, the smaller the mechanical system. And it's dramatic. A really leaky house will need a much bigger system to maintain comfort inside the house, and that costs money. So if you can minimize it as much as possible, then you go a long way to reducing the amount of the size of the heating system that you need to as small as possible. Another benefit to air tightness when we look at attached units, now it's not just the energy penalty that comes with air leakage. If you're in a townhome or an individual unit of an apartment, the air that leaks between the units will also cause discomfort because air that leaks between the walls will allow noise to transfer through. It'll allow smoke and odor and fire, perhaps, to come through. So the more airtight each individual unit is, the better it is for the occupants. And of course, energy efficiency comes with all of that. The Passive House standard sets a target, just like most other programs that have energy efficiency in mind. Even the building code sets the standard. It's just one of those programs that doesn't actually mandate air tightness testing, and so we're kind of just guessing. They set an assumption of what the air tightness target should be, and builders have a checklist of what components could add up to great air tightness, and it just gets checked off, but it doesn't actually need to get tested. Programs like EnerGuide for new homes or even for retrofits require air tightness testing. Energy Star for new homes, Net Zero, R2000, and of course the Passive House standard. They just set different targets, so they allow more wiggle room for that program for the project to achieve. Ultimately, the goal is zero. We want it to be as airtight as possible. It's just challenging to begin with, but what studies have shown and what history has shown is that when you start testing, even without a target, people are competitive. So once you start testing, it's just innate in us that we want to get the best score possible. And so we develop ways of achieving that so that it's replicable, easily replicable, and at the lowest cost possible. So great attention to detail. It all starts with the design. to be honest. That's a big component of it. So if the design is easy to read and easy to follow, then it sets the project up for success. But then it's also the installation. So you could have all of the best details, all of the best products, and if the people who are installing it don't care or aren't doing it very well, then it's not going to be very successful. Supervision, because of that, supervision is the next key part. If people aren't supervised along the way and the supervisors don't know what to look for, then holes can be left and perhaps forever, and things get covered up and the access to it is gone. So supervision is key, and of course testing. You have to test often. You have to plan to test as early as possible and as often as possible until the project team is very comfortable with it, and then they're very confident that they will be able to achieve great airtightness. So all that comes into it. I don't know if anyone's familiar with the blower door. Have people seen blower doors? Blower doors, yes. So you're all kind of familiar with it. One thing that I really like about the Passive House standard is that they don't only need to do a depressurization test. So we're sucking air out of the house, and where there are holes, the air is leaking into the house. They also require a pressurization test. So now we're blowing air into the house, and something that may have closed shut because of the depressurization direction may now blow open. So it's important to test in both directions, and I quite like that about the Passive House standard. The air tightness, it's critical when you're looking at air tightness to make sure that you minimize the amount of holes that go through or the penetrations that go through the enclosure or the primary air barrier, so that you set the project up for success as far as that goes. Is anyone familiar with the metrics with respect to air tightness? Somewhat, okay. So ACH is the main one, air changes per hour. It's a volumetric one. There's an NLR as well, which in imperial is the CFM per square foot of enclosure, or in metric it's liters per square foot, liters per second per meter squared. The ACH one is the Passive House one, and it's 0.6 ACH, which is great. The super tight target. That's a really difficult one to achieve, but easy once you get the right components together and the right strategy, and you do it, test it, and do it often. 0.6 ACH is volumetric, meaning that the air changes per hour. When we test the building, it's at a certain pressure at 50 pascals, which is essentially the same as a 40, 50K an hour wind on all sides of the building at the same time. At that pressure, the house will lose its volume of air 0.6 times every hour. So you can imagine if your house or the building was 10 ACH, that's a lot of volume of air that's leaving the house when the wind is blowing that hard, which I'm sure that happens a lot in Cornwall. And so you can imagine that when that air leaves, it needs to be reheated. And so that's the energy component of it, which goes into all the energy models to help calculate the energy usage of a particular project. So super, super important. Where it gets tricky and where Passive House projects in the past have struggled with it is there's something called the small house penalty. So the smaller the volume of the unit that's getting tested, the more difficult it is to achieve that 0.6 ACH. The bigger the building, like this complex, would be relatively easy to achieve 0.6 ACH, which with much larger holes. So there's pros and cons to that. It could achieve the target, but there could still be a lot of air leaks left behind. So there's the other metric that's called the NLR, or the normalized leakage rate, and that's the same testing process. It's just that we're using different metrics. So when we do the air tightness test, we get that flow of air through the blower door at that 50 Pascal pressure. And so that flow in either CFM or liters per second, that gets divided by the shell of the home or the building, and then we get that normalized leakage rate. And so this takes away that small house penalty, meaning that if a house was really tight, had a really low NLR, but didn't quite meet the ACH target, it might get 1 ACH, but it still meets the NLR because it's a normalized metric to say that it's still really tight from an air leakage perspective for the shell of the house or the building. Meanwhile, a really large building like this, to hit a stringent NLR target would need a lower ACH. So maybe like 0.3 ACH, depending on the target that's being set. So in other programs like the FIAS program or even the Canadian program, so the Energy Star or Net Zero, there are several metrics that can be a pass-fail, and as long as one of them passes, then the project gets their stamp of approval. So it could be ACH, it could be NLR, and there's some flexibility there because of that geometric differences. So that's important to know from that perspective, and I think that does it for my part. Okay? There you go.
Perfect.
I should give this back to you.
Oh, yeah, thanks. Awesome. Okay, perfect. And yeah, back to the metrics that Stefan was talking about too as well. For super insulation or exterior insulation, we're looking about double the amount of insulation that is required for passive house versus minimum building code. So just to give you an idea of those metrics. So we're going to move on to principle number 3, which is high performance windows. So everybody's familiar with windows and doors. These are the elements that allow you to see outside, allow you to open the doors, exit your house. And we do have different methods or different types of windows and doors. There's plastic, PVC, wood windows and doors. There's some that are hybrids, which are both wood and aluminum on the outside. And there's also components in the windows and doors, such as glass. I do have an example here, and I'll toss that around. Just be careful, please, because one of the glass panes is broken, so just don't play with it. I think we're all old enough not to play with it here. Did we make them sign a waiver, Angie, before? No. So whenever you see this window, it's going to be a little bit more robust than your standard window. It's going to be a little bit more heavier too, because there's a lot of components in the window itself. So the key features of the windows and doors, typically they're triple pane windows. So when I say pane, I mean a piece of glass. So there's 3 pieces of glass. And your normal windows that you're going to get that meet minimum building code is two panes of glass. So that triple pane of glass just adds to the overall thermal performance, which again, our exterior insulation is part of our envelope, which is the windows itself. So that adds to the thermal performance of the glass so that it makes that window system that much more robust and better, because 60%, I believe it's 60% of your heat loss is through windows and doors, because you can understand that those are openings that don't have that amount of insulation that your exterior walls have. So triple pane filled with some gas inside the windows, usually argon gas or krypton gas. They have a low U value, so sometimes we can confuse ourselves with R and U values, and I'm not going to get into the nuances of the terms. But whenever we talk about U values, typically the lower is the better, R values, the higher is the better, okay? So our U values is usually, or for a passive house window certified, is less than 0.8 watts per meter squared Kelvin. Your typical building code windows are 1.6. So again, we're on the same theme of double the performance in any case, all right? So that's one of the other key features. We want to make sure the glass pane or the insulated glass unit has, there's spacers that separate those glass panes. So that's a location where there's going to be some heat loss too. So some of those spacers that are inputted into the unit are actually important, and they're typically certified. So all of these windows too as well, typically they are certified with Passive House Institute. So they go through rigorous testing and data retrieval so that they can, they'll put them on their database, and then individuals like designers can specify these windows and use the data for our energy modeling. So the spacers is another component. Again, as I mentioned, gas-filled, so argon, high-quality frames. So you see the one that went around is a UPVC, which is a recycled PVC, so it's stronger than typical PVC. And inside, you probably seen there's some insulation that is stuck in the holes too as well. So that adds to the thermal value or the thermal resistance of the window frame too as well. So it just makes it that more robust. But again, you can have wood and wood aluminum composites, so some combinations. Just to touch base back on Stefan's discussion on air tightness, well, we want to make sure that these windows are sealed appropriately too. Whenever you open them and close them, of course, sometimes windows don't close properly and you get air leakage from those. So with the Passive House certified windows.
If you present it to the camera for those online.
Oh, perfect, yeah, okay, hang on. Let's showcase. Our friends at NZP Fenestration, Montreal. Shout out to them for sure. So hopefully everybody's seen that. So air tightness, I mean, these windows have multiple locking components. So that contributes to the weight of the window in that case, which then allows you to seal the window appropriately so you're not getting that air leakage. And that also contributes to noise control too as well. So again, there's a lot of common themes that we're discussing with Passive House, and that noise control is then mitigated by closing and sealing these windows. And then finally, there's the solar heat gain optimization. So of course, we want a lot of windows. There's a misconception sometimes, and it's true. We see a lot of passive houses that don't have a lot of windows. Well, the main reason is because they're the main contributor of the heat loss. So of course we don't want a lot of windows, but we do want a lot of windows because we want to see outside. We want to be with nature, of course. So typically what we would see is a lot of windows facing southwest orientation. And the reason for that is that we want to take advantage of our free heat, which is solar heat from the sun. So we do have particulars with respect to, we call it a solar heat gain, which allows that solar heat to come in, but doesn't allow it 100% to come in, because what will happen with that is you'll get overheating. You know, we have a big wall of windows and you get a lot of sun in. Well, it's great in the winter, free heat. In the summer, you're gonna cook, right? So then how do we mitigate cooking like that? Well, then you need active cooling, which then costs more money, et cetera, in terms of electricity. So what we end up doing is the solar heat gain coefficient is a metric that we can adjust based on the window itself and the coatings on the window, so that we don't get that intense overheating. And in addition to minimizing that overheating, we also like to play with, or not play with, but we like to utilize shading components. So because our sun is at a higher horizon or elevation in the summer, our shading then will shade our windows in the summer, whereas when it's lower in the winter, it'll let that sunlight come in any case. So we like to utilize shading components too in that sense. And we can also utilize indoor shading operations like blinds too as well, if necessary. I mean, that does contribute to privacy too, which is great. So again, the benefits of high performance windows is you're saving energy because you're reducing your heat loss. So you're not paying as much money to keep, again, fuel running. And sorry if I sound like a broken record, but we'll keep we'll keep repeating those elements. Thermal comfort, again, if you were in a cold climate here, so and it's sunny out, but it's snowing outside, you know, sitting on your window ledge reading a book is fantastic. You can see outside as you're in nature. But you can't necessarily do that when you have poor performance windows because you're going to get cold in a way. So with the respect to passive house windows, you're going to be able to sit beside a window without feeling a draft and enjoy those views. Noise reduction, as I mentioned, so outdoor noise pollution, your noisy neighbor. Environmental impact, again, we're reducing our fuel use, so we are then helping the environment. Durability, so of course, we want to make sure these products last. I mean, we're going to be paying a little bit of a premium for them, don't get me wrong, but they will last longer than your typical windows that you can get from a box store because they are made more durable. And of course, they will increase your property value, so, you know, putting money into the house will get you some money back as well, right? So those are windows and doors. So I'm going to toss it to Stefan again for thermal bridge.
All right, thank you very much, Brooke. Okay, so thermal bridge free construction. Why do we want thermal bridge free construction? Well, a thermal bridge is essentially a discontinuity of the insulation layer. More commonly, we see this all the time in standard building where we build a wood stud wall and then put insulation in between the studs. That insulation has a certain R value. The wood stud has a lower R value, so it interrupts that continuity of that insulation value. That's a typical thermal bridge, and we can't avoid that with wood framing. We need that as a structure, and so to compensate for that, we need to add more insulation, typically on the outside, could be on the inside, it depends on the project, but we want as much continuous insulation that's as thermal bridge free as possible. And that comes with design and appropriately modeling the project to determine how much super insulation is required for that particular project. So there are ways that you can, and that's the simplest way of doing it. If we look at the walls, adding more insulation to the outside, depending on the products that you choose, will determine the type or the structure or the method with which you add the extra insulation. For example, if you use rock wool or one of the foam products, then you can just attach it to the outside with the appropriate structural methods. You could also choose to do a larsen truss where you hang an extra wall on the outside and fill it with dense packed cellulose. That method also creates a thermal bridge free construction to limit the amount of thermal bridging that happens. So that thermal bridge is, if you go back to that sort of idea of that discontinuity of the insulation, it means that more heat can escape through that thermal bridge. So it's like a thermal bridge highway, so to speak, or a heat loss highway. And that could create issues with the house, whether it's from the inside, discomfort because of colder surface temperatures, and of course, heat loss contributes to a higher energy bill. So we want to minimize that as much as possible. It's taken into consideration already when we do an effective R value calculation. So just to put some terminology there, there's when we look at an assembly detail, we can either look at the nominal R value, which is all the insulation parts or all the components that make it up. So and we just add that up so that it's, you know, R20 plus R20 is R40. An effective R value calculation takes into consideration the thermal bridging of the studs and then reduces it on a weighted average calculation so that maybe that R20 layer is actually like an R15, and then the second R20 layer is a continuous R20. So now your effective R value might be 35 rather than 40. So there's a way of calculating that when we're looking at assembly details. When we're looking at other components, so thermal bridges can be three-dimensional as well. It was passed around earlier, this raft slab, or maybe I'll show it here right now. So this is an opportunity using a product like this in a slab to make sure that the floor-to-wall connection of a slab-on-grade product, or maybe this is below grade as well, that this is as thermal bridge free as possible. Because the insulation is as continuous as possible from underneath the floor, around and up the walls. So that's what we mean by thermal bridge free with respect to components like that. But that happens all the way around the house, in all junctions. And when we look at it from a passive house perspective, we have to calculate that. And there is a definition with which we can apply or determine if a junction is thermal bridge free. We can do the calculation. We can use a software called Therm to measure this and put a value to it that we can then put into the energy model to account for these thermal bridges. Now, there are some positive thermal bridges, which I feel like it's backwards. So a positive thermal bridge is bad, a negative thermal bridge is good, or something like that. In any case, there are some thermal bridges that are bad, some that are good. For example, an outside corner of a house is a good thermal bridge because there's more insulation, but an inside corner actually turns out to be a bad one. So a little bit of a nuance there, but that's just with respect to the calculations. Another really key thermal bridge that we see all the time, and certainly as we're driving around cities right now, and skyscrapers are going up and there are concrete balconies that stick out, well, that concrete, not a very great insulator, and if it goes from inside to outside, ends up being a really big thermal bridge. So if that project was pursuing passive house and it has that big thermal bridge, it would need to account for that, and perhaps it works out that it's okay, but if it isn't, then the project team would need to come up with strategies to overcome that. So that's the great thing about the Passive House program, is that it does highlight the need to calculate these. But it's time consuming, and so most projects don't pursue that, and I think in BC they've come up with catalogs of thermal bridges for typical details, and if it looks a certain way with a certain strategy, then it can be applied to the energy model as a particular type of thermal bridge. So the industry is starting to grow as far as that goes, and identify this as an issue and come up with strategies to make identifying thermal bridges easier and overcoming them at the design stage. Because when we start building it, then it's difficult to change course at that time. Other areas where thermal bridging happens, as Brock mentioned, with the windows. Windows end up being the weakest point of most buildings, especially that glazing to frame part of it. And so we have to do the best with what we've got. At the end of the day, there's got to be a weak point in the building, and that just happens to be it. So there can be strategies with which we can minimize that thermal bridging of the frame. And fortunately, with frames like this, where there's a lot of room here, we can actually do some over insulation so that we can minimize the thermal bridging that's happening because of this weak spot of the house. Even though if we use a product that's as good as this that we're showing, there's still ways to make it better and eke out more kilowatt hours and save more or waste less from that perspective. Other thermal bridges that we see often, and similar to the balcony of the commercial, but now if in the residential side of things, if beams go out from the inside to out, well then that's a thermal bridge that needs to be compensated somehow. Oftentimes we'll see beautiful designs where there's big cantilevers out. Well, in order to get that structure to go out, steel or some sort of member needs to go out, and if that's not encapsulated in insulation in an appropriate way, well, then it represents as a thermal bridge as well, which will be there for the life of the building. So we want to make sure that that's taken care of early in the process. So the key benefits of reducing the amount of thermal bridges that are in a building, obviously reduced heat loss, indoor temperatures, like I said. If there are some thermal bridge connections that when we model it in the software, it can give us a sense if there's a risk of condensation. So another nice reason to go down that route of identifying these sort of thermal bridges and compensating for them is, efficiently at the design stage so that it passively takes care of that condensation risk. And so we don't want that moisture control, occupant comfort, and obviously building durability as well. So you can see there's a common theme with all of these elements of a passive house where it's all about durability, comfort, and moisture control, and the byproduct typically is energy efficiency. So wrap that all into one, and we've got a great solution to build great buildings or to retrofit to an appropriate standard. So that's it for thermal bridging. There you go. Oh, and I guess there you go.
Yeah, I need both of those. Next slide. Mechanical ventilation with heat recovery. I'm Jeremiah Point, founder of Point Engineering, based out of Akwesasne, right across the river. I also own another company, Nova Commissioning. That's the shirt I'm wearing today. Came straight from work. Certified Passive House designer, as well as a licensed mechanical engineer in Ontario. I work local in the area with many different groups, especially with Brock Wilson, especially on the front for passive house design. I was certified passive house before Brock. I just want to make that clear because he was the second one in Eastern Ontario. But it's been great working with him and really pushing the industry in this local area to start adopting this. We have several builds in the area that have jumped on board from the homeowners directly and adopted these principles, and they see the benefits from it now. They're actually living in them, and they just can't stop talking about it. So we don't really have to sell it as much anymore directly because they're selling it for us. And it's really just a concept to adopt on approaching the construction of buildings in a different way, a smarter way, a better way. And there's, as you've seen so far, there's plenty of benefits to accommodate for that. For the mechanical system, once you start incorporating all of those items and concepts for the building envelope itself and reducing the leakage of the house, what we always get from early adopters or talking to different people who aren't familiar with this is they say the house has to breathe, the building has to breathe. It can't be airtight. Yes, but let's make it breathe the way we want it to breathe, with control, with energy recovery, with maintaining that heat within the building. So you can see there, number 4, the mechanical ventilation unit. So when you're exhausting that air out of the building, previous building code versions would require some kind of an exhaust fan. So you're taking warm air that you heated up, that you paid for, and ejecting it directly outside. That's a waste of energy. So you can make your building airtight, but if you're exhausting the air out, you're just throwing that energy out the window, basically. So building code now requires energy recovery in those units. So you're bringing air in, but you're also taking the stale air out. And as they pass through the core, like this one here, that I scavenged from an older unit, the two air paths don't actually mix. So they keep separated by the cone, the honeycomb shape inside, so that they're passing through with a very thin layer between them. So that can, for a HRV, will recover the sensible heat and just the temperature, basically. And then for an ERV, which is better for Canadian climate, it will recover the moisture as well. So you get both forms of heat, both the dry heat and the moist heat. And so I believe this one's from an HRV. So the ERV will have a different coating on the membranes. It's a little heavy. That one there is from a typical standard unit that's being implemented from previous building code versions. And as we start looking at passive house, that's actually not good enough. So the core will be elongated to give more time for the heat to exchange between the two air streams. And that will give you a higher efficiency. So typical units are like 60, 70% efficient for recovering that heat. You go to an ERV with an elongated core, you might see more like a 90% heat recovery or 95%. With those units, you're balancing the airflow that's leaving as well as entering the building, so you don't get the air leakage through the walls. So even though you make them airtight, there is still going to be minor leakages, but if you balance out the pressures from indoors to outdoors with a balanced ventilation system, then you can filter all of that air that's leaving or entering the house, and you're going to keep any moisture or any unfiltered air from traveling through the cracks and the small leakages in your wall assembly. So most houses that were built in the 80s, when you start pulling the siding off, you see the rot and the mildew inside underneath all the windows, especially in the corners of the windows, just because of poor air tightness, but exhaust-only ventilation, which is pulling that cold air through those cracks in the wall assembly. Once it meets the warm, moist air indoors, it turns into condensation. And that's why you get the black on the OSB on the sheathing layer. That's why you're getting all of this rotten mildew inside the walls. And then at some point, if it's bad enough, you have to open an entire wall and replace everything because it's got structural damage. So by incorporating these principles, you can start eliminating a lot of those problems, using your ventilation unit to actually control how much air is going to be exchanged in the building so you can get proper ventilation. And then by incorporating that, you're going to minimize those problems in other areas of the building. So taking all that, I know it's a lot, what we're looking for, especially in a passive building or something that's more energy efficient, you're going to decouple that ventilation from the furnace. So in a passive building, you eliminate the furnace. So you can imagine double the insulation of your house, your furnace is half the size. It's a direct result. You eliminate the air leakage, you reduce the furnace even further. So incorporating some of these concepts in an intelligent, cost-effective way, you can eliminate the furnace completely, and now you're just left with the ventilation unit, and now you've achieved the passive house standard. So that's what we're trying to achieve. We're going to ventilate very controlled, directly to what we're trying to achieve, calculated airflows through each room of the house or the building, so you get that proper fresh air into the building. So that requires all of your ductwork and all of your air exchange, and everything gets much, much smaller and saves some floor space inside. People like to say, well, you got to have a furnace. You got to have, because we're so ingrained to believe that. But when you go to other countries where they pay 3 to 4 times more for energy than what we do, they've already incorporated all of this, especially in Europe and Germany and different places like that. So keeping that in mind, you're reducing how much mechanical systems you actually have. As a mechanical engineer, traditionally, the architect will make up a floor plan, they'll pick R values out of the building code, they'll design that, they'll hand it over with the window sizes and dimensions to the mechanical engineer. Mechanical engineer will then size the heating system to accommodate. So Passive House is requiring the architects to then do the calculations themselves, see the impacts of the R values, and it's moving away from the mechanical engineers so that it's getting designed up front where we don't require that recirculated heat within the building, and eliminating the dependency on the energy to keep the building conditioned and comfortable. So the benefits of that, your heat savings, your comfort, your moisture control, because the more air leakage you have, you're going to have much more dry air inside because you can't retain that moisture within the building. Most of the code minimum buildings that we have currently with the double pane glass, once that humidity level indoors starts to creep up to like 35%, 38%, you start getting condensation on the glass. So on the really cold days, you start wiping the bottom of your windows with a cloth because you're getting that condensation on there. Once you add that third layer of glass, that goes away. Your humidity levels indoors can be maintained a little bit higher, which is better for human comfort and health, but you're also still getting the proper amount of fresh air because you're using the ERV that's going to retain as much moisture as possible within that building. So it's just benefits overall. So you get your moisture control, you get your energy efficiency from your heat recovery, which doesn't require a mechanical system to recover that heat because it's just a stationary core. Your noise, so you don't have the furnace kicking on and off, blowing warm air on you, then it shuts off, then you feel a cold chill, then it kicks on again. So you start eliminating that kind of nuisance. And then the indoor air quality. So because it's so airtight, that means all of the fresh air coming from outside is going to be filtered. And a lot of these passive units that we use in passive houses, the energy recovery units that we use in passive houses, they have HEPA filtration. And we've seen it already in Canada out west when they have the forest fires in BC. Any of the people that were living in passive homes in BC during those forest fires and during the smoke issues, they didn't have to evacuate because the air was cleaner inside the house than it was outside. And the people that were living in code minimum houses, they had to evacuate their homes because they were having respiratory problems. So that resiliency, especially for climate change for them where they have a lot of forest fires, and we're seeing that more in our area as well in Northern Ontario, Northern Quebec. So it's something that's probably going to keep happening more and more. So, and filtering that air before it comes into the house and being able to control it and filter all of the fresh air coming in, you won't get that smoke infiltration through the leaks in the walls themselves. So that helps with the air exchange unit to balance out that pressure as well. Every time the wind blows, you're still maintaining the proper airflow in the building because you're not susceptible to that pressure difference. The harder the wind blows, the more it breathes. And that's the energy efficiency or the cost component where I'd rather have a building that I know what the energy bills are going to be regardless of what the weather is outside. Where a leaky house, the harder the wind blows, your energy bills are then higher as a result. So you're susceptible to those weather patterns. So once you start incorporating these, even power outages become less of a problem because you really just have to look at how much fresh air you're bringing in and not to keep the furnace running or not to keep the heat going in the building. It'll go much longer without the requirement of that energy in order to stay within the building itself and still have the indoor air quality and the comfort that's retained within it by having a resilient building overall. What am I missing here? That's 10 minutes. Kind of cover a lot real quick. I seem to talk fast. Talk about the hair dryer? Oh, so what we've seen for our cold climate here, those energy recovery units will go into a defrost mode when you start hitting the minus 20 Celsius. So to prevent that, we put an electric duct heater on the fresh air intake between the unit and the outdoors. And that'll temper that air to keep it at, say, minus 10 Celsius, whatever the unit requires. And then you maximize your energy recovery through the unit. And then at the discharge of a unit, we put another duct heater to temper that air to room temperature. And then you calculate to maintain the building temperature for that, and that's what designs basically the R values of your walls and the building assembly. You have to have the air exchange no matter what. But the duct heaters that we're putting on there are like 1,500 watts, the same as a hair dryer. And so literally, you're heating your house with the equivalent of a hair dryer. And that's what's keeping the house warm. Now, that's extreme when there's not enough people in the house, there's nothing else running. But as a mechanical engineer and doing energy modeling previously, before it's getting kicked over to the architects, every human body is about 347 watts of heat being generated. The refrigerator's about 420 watts of heat being wasted. Your TVs have waste heat. Your computers have waste heat. The lighting has waste heat. So the better you seal up that building to keep that waste heat inside, the less you're going to depend on those mechanical systems. For our climate here, particular in SD&G area in Eastern Ontario, we get really humid summers. So we get kind of the worst on both. We get extremely cold winters, really humid summers. So we still have to have some form of dehumidification for the summertime. So we like to go to a ductless split, the smallest one you can buy on the market because you don't need much more than that. So we see a lot of Mitsubishi, a lot of Daikin units, Fujitsu, but we opt for not just the air conditioning ductless split that's going to provide that dehumidifying in the summertime because the temperature will be fine. We're not just dehumidifying, but let's just get the one that's a heat pump as well for cold climate conditions so that we can get heat out of it in the wintertime and use it year round. So then you can just put the settings on the thermostat and then just forget about it and let it run. Because as you seal up a leaky boat, you start with the big one, the big leaks first. Air leakage, the windows and doors, the R value. And then you start looking at the small leaks because you've done all the work for the large leaks. So then we get down where we like to kind of geek out, and we get down to, well, we have 1,500 watts on the air exchange unit that's providing our heat, and that's just straight resistance electric, 100% efficiency. For our area, we're on hydroelectric power, which is great, renewable energy already. Then we put in the heat pump, and we can basically turn off those duct heaters and use the heat pump instead, which is going to give you a 2 to 3 ratio. So for every 100 watts of energy consumed, you're going to get 200 to 300 watts of heat in your building. So now we're splitting hairs because we're talking 1,500 watts total. Well, now we can get that down to maybe 500 watts of consumption. So now your energy bills are like $150 a year to keep your house warm. So it's just every time we chip away at something and we use these methods to incorporate in the building, and we start with the worst ones, the windows and doors especially, because that's your weakest point. Then we start with the building envelope. I'm kind of getting into the conclusion part of this. Let me scroll ahead. Oh, I guess we don't have a slide for that. So with incorporating all these 5 principles that we've talked about through the Passive House, what we like to do is bring our hands-on approach. Like, we've been in construction, we've built things, we've used our hands, and that kind of gives us a leg up on other designers and other engineers who may not have that hands-on experience, and using that practical knowledge of direct construction experience to incorporate these methods into and concepts into the building construction in a practical approach. So I have a sample over there in the box that I'll put out on a table later. It's a block of hempcrete. It's great, people love it. Oh, hempcrete or SIPS panels or something like that. And it's like these expensive materials that we're going to incorporate. And I got LEED certified years ago, like 20 years ago. And what the LEED certification did for leader in energy efficient design really sold the concept that building energy efficient buildings was expensive. We put geothermal, we put solar panels, and we spend money on these very expensive technologies to offset our energy consumption of the building to achieve, and you hear it now, the net zero concept, where you could have a wasteful building, throw a few $1 million of solar panels at it, and now it's net zero because you're not consuming more than you're producing on site. But it's very expensive to do that. It's a lot of maintenance, a lot of upkeep. As a mechanical engineer, I still don't think the solution is a mechanical solution. I think it's an architectural solution. And that's why I really was drawn toward the Passive House concept. I actually joined the board of Passive House Canada for the last 6 years, just to drive home that idea that you can build energy efficiency, you can have comfort, you can have very high indoor air quality, cut down on your allergy medications, cut down on the dust inside your home, the air leakage, make your building last longer, and incorporating all of that. But in a practical sense, using the materials that are available in your area that's readily available and low cost, using the labor force that's there, which we've been trying to push to train the local labor force to start thinking about these things and incorporating it. And what we see with different contractors and builders is that once they take the training and they understand what Passive House is, they can't undo it. They go back to building a typical home or a typical building, and they're still thinking about it and still incorporating those ideas into their construction no matter what, for the air tightness and the leakage and water infiltration, and they're still thinking in that way. It's once you get educated about it, it's hard to unsee it after, and you really start to look at every building. You see them going up in construction and you just kind of cringe a little bit when you drive by now, because it's like, oh, that looks so bad, because you know better. And it's really just access to information and access to the proper knowledge to incorporate it. I've worked with some architects, not Brock. I've worked with some architects where they come up with extremely complicated wall assemblies and window junctions and thermal bridging approach that really doesn't really drives up the cost, and it really puts a lot of emphasis on the labor that's doing the installation to do it properly. They're using tapes, they're using membranes, they're trying to layer things up. If the tape doesn't hold for the next 50 years and it starts to delaminate after 50 years, well, now you've got a new leak in an older building. And we really want to utilize the materials so that we don't have those problems down the road, because we all know, whoever's been through a renovation, Jesse's going to talk about that, it's expensive. To redo a building with a major renovation costs a lot of money. So with the Pass House concept, it's building it right the first time so we don't have to go through those painful renovations later on down the road. I'd rather shift the money away from mechanical systems that are going to last maybe 15 years and put it into windows and doors and wall assemblies that are going to last 50 years or more. So it's just working within the same budget, and that's what we try to bring it to our clients and customers is, what is your budget? What size of a building you want to build, and then we just work within that. So instead of spending $30,000 on HVAC systems, we trim that back, and we take the savings from not having a furnace and large ductwork, and we shift it towards the windows and doors. So you're just moving money around within the same budget if you can approach it with a practical point of view and incorporating these concepts from the start, including in the design up front, because as Stefan mentioned, when you try to pivot and change something during construction, it's really expensive, delays in schedule, causes problems down the road, and you're trying to put a Band-Aid over a problem that could have been addressed during design up front and looking at the details and trying to incorporate these concepts up front. So it can be done, cost on par, but it has to have that practical hands-on approach and using what's available and not trying to shoehorn in something like hempcrete, which I brought the sample, but we have to import our hemp because we don't grow it around here. You go out west of Manitoba, sure, it's in abundance, it's a cheap material, till everybody starts using it. Then it's expensive again. So it's nice to play around with these different materials and whatnot, but at the end of the day, it really all goes back down to what's the skill set in the area and what materials you have readily available. When you see with the external insulation, we're shifting that insulation layer away from the structural layer and getting it out from between the studs and wrapping it on the outside of the building. That means your exterior structure, the stud wall, is going to exist on the warm, climate-controlled side of the insulation for its entire life. Now, that rot and mildew that we see under the siding of a typical home doesn't exist anymore because the exterior structural walls are the same as the interior walls that don't get exposed to freeze-thaw cycles and water infiltration and humidity and leakage through the windows and doors. So we can start to separate that out instead of trying to combine it into a stud wall assembly with batt insulation and losing the R value like Stefan mentioned, and separating those out, that we have an insulation layer that's clear on the outside, we have a structural layer that's clear on the inside, and not really trying to mix up the two and compromise the building envelope overall. So having that practical approach, and we'll go into some breakout sessions. We'll let Jesse talk about his personal journey for his home renovations, and then we can have some open discussions about maybe what problems that you've seen directly and ask questions. We can propose some solutions. We can talk about further investigation, and just especially home renovations like Jesse's, it's very unique to the situation. We have to look at what the existing building is and then how to incorporate these concepts into it in a cost-effective approach so we don't just blow the budget out and not achieve all the goals and objectives that we're looking for. Jesse?
Thanks, Jeremiah. Hi, everybody. I'm Jesse Good. I'm the chair of the city's Environment and Climate Change Committee, and I am the layperson on the committee. These are all experts, and I've learned so much from them. I'm sure you guys have too. And like I'm sure some of you too, I'm a homeowner here in Cornwall, and I've got the hand I'm dealt with, essentially with the house that I've got. So when I moved into my home, it's on Sydney Street. It's a century home, beautiful construction, kind of like a heritage style. You know, it's masonry. It's got a lot of character and charm. It's got leaded glass windows and original features to the house that I don't want to miss out on. But as a century home, it's got a lot of energy loss. It's got a lot of air leakage, and it has a lot of systems which just don't perform to a modern standard. And so how do you incorporate some of the thinking that we've heard around passive house and adapt it to, you know, the practical situation that you're dealt with as a homeowner? And that's kind of where my journey was. When I started, I just wanted to make it clear that this is a fantastic system, and it strives for the best that's out there. For the rest of us, we try to do the best we can with what we have, and I think that you can take these principles and adapt them in a practical way to your home in a way that doesn't destroy your budget necessarily. It can. Mine was quite expensive, and I'm not sure what I get out of it, but the idea is just that there's a lot of things from this that you can adapt to your renovation process. So my house was built in 1935, heritage home. When I bought it, the furnace was 20 years old. It was at the end of its lifespan. It has central ducting in my house. It's a 3,000 square foot house, so it's quite large. We have a large family. The air conditioning system was also on its last legs. They were replaced at the same time, about 20 years before I bought the house. And so I knew that I'd have to replace the furnace soon. My primary objective is probably different than most, is that I just wanted to eliminate fossil fuels from my life as much as possible. So it was an environmental motivation for a lot of my renovations. So I wanted to get rid of the natural gas connection to my house and fully electrify. So this is my electrification journey, effectively. So to electrify an old home, you need to replace the existing natural gas furnace with an alternative. So I'll just say right away, the alternative in my case is a cold climate air source heat pump, which is connected to my ductwork. It's replaced my old natural gas furnace, and I just rely on electricity through my heat pump to produce all my heating. It also produces all my cooling as well, but that was the one of the main things. I also wanted to, like, my purpose besides eliminating fossil fuels was to maximize the available grants that were available at the time through the federal government for Greener Homes loans, Greener Homes grant. They had generous packages for homeowners that could pay for a lot of the provided incentives for the installation and windows and the heat pump and things like that. I wanted to reduce my emissions. That was like number one purpose. When I bought the house, it was the fall. I knew that the heat pump or the existing furnace could die any time, and if I didn't plan ahead, here's the thing, you get stuck, right? You get what's available on the shelf, and like the guys were talking about, the local contractor knowledge. Local contractors are most comfortable doing what is there already. They'll replace your existing furnace with what was there, before. And for most homeowners, that's fine. But I wanted to get ahead of that process and not get stuck in a situation where the equipment that I need to have on hand wasn't available. So I basically said, okay, I bought the house. I know I've got to replace the furnace. So let's just go down this heat pump route. There's all these grants available. Let's do it. I started with an audit, an energy audit of my house, which did the blower door test and all that stuff. Part of the energy guide or EnerGuide process for labeling homes is doing these tests, and to get the grants, you need to actually do these tests as well. So they did the pre-audit. We were talking about a 0.6 air changes per hour. My Century home at the time was about 9.3 air changes per hour. So quite high. I mean, I'm heating all the air 9.5 times right before in 1 hour. It's absolutely crazy. The emissions of my house, calculated by the technician at the time, were about 10 tons of greenhouse gas emissions annually from the natural gas that I was consuming from my furnace. So I knew I needed to install a heat pump. I needed to get the energy efficiency up in my house as much as possible, and there's a few different ways I approached that. So number one was insulation. Attic insulation was very poor in my house, probably only R10, R15. I brought it up to R60 with blown-in cellulose in one attic, and another attic which was really prone to air sealing issues. I actually did a layer of closed cell insulation and then topped it with blown-in cellulose to get that R factor, but not spend a ton of money trying to get that R factor through the closed cell stuff. But that really did improve the air leakage through that particular rough area in my house. Insulation was huge. We actually had a big gaping hole in the wall, which was an obvious thing to fix, right? But when you have a masonry house, there are very limited things you can do. You can't add new insulation on the inside of the wall because you'll lead to possible issues with condensation. These guys can talk to you about all the reasons why you can't do it. I only have a layperson's understanding of it, but you can't do tons of insulation on your inside walls. I've got windows that can't be replaced because they're, characters of the house. So you do everything you can, right? So obviously the big hole, filled that, changed a couple windows and doors, which were really problematic. And as you talked about supervision, even in just the process of explaining to people, like, my goal here is to get the most energy efficient new set of patio doors here possible. Can you do it like this, like I've seen on Matt Reisinger's build show? You guys probably all know that. So here's the technique I want you to use. Send him the video. This is what you do. And it's just like they're scratching their head. It was difficult. So it required the supervision for me to tell them what to do, which I'm not really qualified for. So a little knowledge is a dangerous thing. So I think along this process I probably made a lot of mistakes, but it's really not about doing it perfectly. So upgraded the installation. What I really wanted to do though is sequence the renovations in a way that would save me the most amount of money. So I had a separate issue with this entry house. The weeping tile system had to be replaced. But it provided an opportunity to insulate from the outside, right? Take advantage of another renovation that I needed to do. We excavated around the entire house to fix the weeping tiles. At the same time, put rock wool all around the outside of the exterior of the foundation to improve the R value of the basement. Basically, my key message today is that the improvements you can make yourself by doing them incrementally. When it dies, electrify, like get rid of your natural gas and replace it with a cold climate heat pump. Take advantage of these opportunities where you've got these renovations to kind of plan ahead. So if you need to, for example, if you're planning on getting an EV in the future and you know that you may need to increase the size of your panel, maybe you also are going to consider your heat pump needs in the future too. So make sure you size everything correctly and plan ahead. So long and short of it, my house is now fully electrified. I only have one energy bill. It's just my electricity bill. The air changes in my house, I've reduced them from 9 to 6, so a big improvement. But I bet you guys could probably teach me lots of ways of improving even more. I've reduced the emissions of my house from about 10 tons a year to about 1 ton a year. So that's a huge deal. And yeah, I will just say that the challenges were, it was very expensive along the way. Especially navigating the policies of the grants and the loans and the uncertainty of how to apply for them, carrying those costs to then get the grants back and things like that. It's not something everybody can do. So that's why I encourage like small steps and to think about air sealing as like the number one. Because if you can reduce the amount of uncomfortable cold air coming into your house, you're going to make a big difference. And I'd say that's my personal journey. Thank you very much.
Thanks.
Sorry. Thank you, Jesse, Stefan, Jeremiah, and Brock. Before we do go to the breakout rooms, we're going to quickly check and see if there's questions online. And if you do need a demo site, I have a century-old house that's 850 square feet that has shifted, and there's tons of cracks. The mice have discovered them all. If you need a demo site, I'll volunteer my little house for you for retrofit. Are there any questions online? Okay, do you have any, before you go into the breakout rooms, any general questions that, perhaps everyone can benefit from if you were to ask it now? Jackie? Oh, one sec, we're gonna give you a mic so they can hear you online.
Can you hear me? Oh, is it for there? Okay. So I understand this is passive house building, correct? Okay. So I was kind of hoping to hear something about passive solar. That does not incorporate passive solar?
Okay, yeah. Great question. So the question was, does it incorporate passive solar? So yes, it does. Back when we were talking about the windows, for example, we like to orient houses to as well in that specific southern west location so that we can take advantage of that passive solar energy for sure. So in addition to all of the other things that we talked about today, we do incorporate passive solar as well. In addition to that, and Stefan can talk more about it in our breakout room if he wants to come up here, is orientation of your house too in terms of your roof pitch, so that you can then also take advantage of renewable energy like solar panels too, that can then be incorporated into your house and then really get you to a net zero certification or label. So whenever we talk about net zero and net zero ready, there is particulars required in terms of meeting better efficiency of your house and getting testing and all that for air tightness to hit that label. But we also talk about hitting a passive house standard, which essentially is reducing your heating demand or your energy consumption by 90%, which you've understood in terms of a cost-saving ways. Doing so, then you can understand that the renewable energy resource that you have to produce is then also reduced at that same time. So there's a lot of cost savings in addition to that when you go for a passive house approach. So hopefully that answered your question.
Well, I guess, because you talk about thermal bridges. Okay, this one. You talked about thermal bridges.
Yeah.
Okay, so that is the heat leaving the house through that thermal bridge, correct?
Correct.
So I was thinking okay, that thermal bridge could also work the other way, right? Like the sun heats the thermal bridge and it goes in the house.
Yeah, that's a good point.
Yes, that's possible?
Potentially. Yeah, that's a good point. I'll give it to Jeremiah.
Sorry, I'd like to speak on that. The problem is that in Canada, we spend more time heating our homes than we do in the summertime. So there's just so much time spent in the wintertime. It's cold. We can't even get it to a warm spring until probably next week because we got snow last night. But when we do our calculations, energy modeling, the energy model has to be ran for the worst case scenario. That doesn't mean minus 30, because at minus 30, the sun is shining. So if you're doing passive solar, then you're trying to incorporate that sun shining. But the worst case scenario might be when it's not really that cold, but it's cloudy in middle of the night. Now you don't have that benefit of the solar gains from the sunlight. So the first modern passive house that was built was in 1977 in Saskatchewan. It's called the Conservation House, and that was studied in depth. They incorporated a lot of solar gains from the sun, and what they found was the whole overheating issue was more of a problem than trying to capture the sunlight, which wasn't reliable, can't be controlled. So taking that data, they went back to Germany and created an R&D center, the Passive House Institute, and they developed the standard from that data. And what they found was we need to not just focus on the sunlight, trying to capture as much as possible, but let's just reduce our air leakage, look at the building envelope, and look at the 5 principles. That's where that all came from. And then the solar gains is really more of a calculation that we're not overheating, because that becomes more of an issue. And then the insulation, you can imagine, is going to work summer, daytime, wintertime, summertime, no matter what. It's going to work all the time for you. So the sunlight isn't always going to be there for you. So trying to eliminate the need for that heat to begin with, we found that you don't need to capture the sun. So a lot of the more recent passive houses, especially the ones that we've done in this area, really don't have any aesthetic look different than a standard home, except the walls are a bit thicker and the windows are a bit more robust. That's really the only difference. They just fit right in the neighborhood. They kind of look the same. People who are aware of passive house, they drive by and look, that's a passive house over there. Because they can tell just by looking at it, because it's a little bit thicker around the windows, you can see the extra insulation. But most houses don't require the sunlight in order to keep them warm. Same thing with in-floor heating and all those other sources. It's just too much heat for that situation. And when we do our energy modeling, we have to use climate data for 50-kilometer radius. So you go a few hours towards Kingston or up in Renfrew, Arn Prior, you go up the valley, the calculations change because we have to use their climate data, and it's not always available either. So it's very specific to the situation. It does cost more upfront to do the detailed energy modeling, but it does pay you back over the life of the building. So you end up with a building, instead of lasting 25 years and need a major renovation, maybe 40, 50 years like Jesse's place, and then you need a renovation, you just can't help but do a renovation because it's so wasteful on energy. Well, if we're looking at those 5 concepts and incorporating them up front, you can go 50, 80 years and not need a renovation. Now you're just looking at items that don't have moving parts that need to be maintained and replaced. Like probably the weakest point is going to be the seals on your windows. So looking at the passive solar aspect starts to disappear really quickly when you start crunching the numbers and really pinpointing where the issues are. So one of the big ones, like going on and on now, like Jesse's place, the masonry on the outside. And they did that in New York City. They started insulating on the inside, destroyed the masonry on the outside because of the freeze-thaw cycle. Because the heat from within your building is leaking through that exterior masonry to keep it warm so it doesn't get saturated with water and then frozen, and then just destroying the grout in between and the mortar in between the brickwork or the stonework. And heritage buildings were destroyed in less than a year because they insulated too much from the inside. Now, trying to keep it warm enough to keep those stone and bricks dry on the outside of your building is expensive for energy, because that's all heat that you're paying for leaking out through the walls to the exterior masonry to keep it dry and keep it warm. So probably get rid of the masonry and just look at pulling it off and replacing it with insulation instead from the exterior. You have the space for it. So those are different concepts that Jesse's itching to ask us about, as well as your place, because we have a lot of masonry buildings that need to be addressed. And that's one of the most wasteful things, is putting masonry on the outside. We have modern masonry now that's not a full thickness and full weight, but more of a cast brick and cast stonework that really looks close to the real thing. You can't really tell it unless you walk right up to it. So those are different ideas that we end up incorporating in passive designs, because people still want it to look the same. They want that catalog. This is what I want it to look like, but then we can take the catalog and revamp the internal structure that you don't see and the concepts and incorporate those and still give you the outside view that you're looking for and the aesthetic of the building itself.
Thank you. So I think this is where we'll say bye to the people who are online, and then we'll go into our breakout rooms. So thank you, the River Institute Science and Nature Speaker Series, for partnering with us for the online portion. So thank you. Have a good